Hi everybody. Today I'm going to talk to you guys about waves, and I'm going to do a quick review of simple harmonic motion so that you make sure to get all of the information that you need for that. So sit back, relax, and enjoy. Again, this should get us ready for the quiz at the end of the week, so you want to make sure that you're paying attention to it. If you need to jot down any notes, maybe fill in the holes in your understanding, that would be good. We're going to start off, as we did in the unit, with a spring pendulum. And if you recall, a spring pendulum finds its equilibrium point. And then if you want to change the position of a bob, in other words, to stretch out or to compress the spring that the bob is attached to, you have to be able to do work. And that force that you apply is equal to the opposite of K times the displacement there. So it's equivalent to that, I should say. The magnitude is equal to the opposite of K times the displacement. K, remember, is the spring constant, and it has to do with how stiff the spring is. As a result of doing that work, you've put potential energy into the system, and therefore, as you let the bob go, that potential energy gets converted into kinetic energy by the time it gets back to its rest or equilibrium position. That kinetic energy then is too much to be able to stop right there, and as a result of its inertia and the kinetic energy, it overshoots the rest position and begins to convert the kinetic energy back into potential energy, and the whole process repeats itself. So this is a spring pendulum, as we talked about, and the equation for that spring pendulum, as you recall, is the T period is equal to 2 pi times the square root of the mass of the bob divided by the spring constant. Now, if we mount that vertically, just for ease sake of understanding here, we can do the same thing, and so we have a spring pendulum that's mounted vertically, so it's going to oscillate up and down rather than left and right. We did this in class, and you may recall that over time, the displacement that it described had a sine wave-like form. And so that's how we transitioned from waves, from oscillations into waves. Now, this simple harmonic oscillation idea is when you have oscillations that are repeated and undamped. In other words, the oscillation occurs repeatedly the same way each time as it goes through a set of oscillations. So it doesn't lose any energy to thermal energy. It's mechanical energy. I mean, that's potential and kinetic stay equal to a certain sum. And so that sum is not decreased as time goes on as energy gets lost to thermal energy. And you can think about this, if you're talking about a matrix of particles rather than a single oscillating bob, you can think about this as being a wave. So as you take one of the particles that happens to be connected to other particles in a matrix or in a medium, if you wish, you can do work on it, which causes it to move, which then causes the particles that are nearby to also gain in potential energy as well. And as a result, the potential energy you put into the system gets transmitted both to the left and to the right. Or in a three-dimensional sense, the energy that you put in gets transmitted in all directions, up, down, left, right, backwards, forwards, and so on. Now there's really actually two kinds of waves, and so I'm going to show you what those are. So you either have a transverse wave where the displacement is up and down, or you have a longitudinal wave where the displacement is along the same dimension as the wave is moving. And so I'm going to go ahead and show you that here real quick. So here we have the displacement of particles being vertical while the wave itself travels this way. So I want you to watch as the crest moves its way along. We can follow this crest as it moves through the medium. But notice if we focus in on one particular particle, that particle is just oscillating up and down. We call that a transverse wave, and there are many waves like that in the real world, including secondary waves in earthquakes, and also the sort of water waves. Water waves actually have kind of a interesting shape to them that's not quite transverse, but for us, for right now, and for simplicity's sake, we could say it was pretty close. So again, energy is transmitted at 90 degrees, at 90-degree angles through the motion called transverse waves. So just keep that in mind. The other type of wave, which is also seen, which you're probably listening to right now as you listen to the sound of my voice, is a longitudinal wave. And that's where you have waves that increase in pressure or density of the particles and then decrease in pressure or density of the particles. And so as a result, you have the particles oscillating back and forth this way as the wave moves along like so. Now, oftentimes when we try to represent sound waves, we represent them as transverse waves because, quite frankly, transverse waves are much easier for the human brain to comprehend. These kinds of waves are not so easy to see. And you're going to see that here as I go back to our simulator. So you can see these are longitudinal waves. As you can see, they're being transmitted. So I can follow a point of high pressure as it goes across the medium here, and so on, and so on, and so on. I could follow it all the way across. Now, what's important to note, though, is that each particle, and so there's a red particle here, and a red particle here, and a red particle here, you can see each particle only oscillates back and forth around a rest position. It doesn't move along with the wave. This is the point I tried to make with the stadium waves, so hopefully you remember that. I could watch this all day. I think it's pretty hypnotizing, quite frankly. But you can see there's a high pressure and a low pressure region. The high pressure region is called a compression, and the low pressure region is called a rarefaction. And we're going to talk about those more when we get to sound waves. So, as I said, sound waves are these longitudinal waves. They're also called compressional waves. So as you see right there, I can kind of go back and forth on it. Compressional waves because they're made up of compressions and rarefactions. Longitudinal waves because they go along the same dimension as the propagation of the wave. There we go. Okay, so some important things to remember: that waves have a period. That's the time it takes for one full wave to pass you by. They also have a frequency, and the frequency is the number of waves that pass by you in a second. And so, as you might imagine, since this has to do with time and this has to do with time, they are, of course, related. And in fact, we find that they are reciprocals. And so the period is equal to 1 over the frequency, or the frequency is equal to 1 over the period. Frequency is measured in oscillations per second, or waves per second, but that's way too much for us to say all the time, so we usually abbreviate it as hertz, like that, which just means waves per second. Period is, of course, measured in seconds. A wave speed, though, is something that is not dependent on the amount that the wave, the frequency of the wave, or the period of the wave. It is dependent on the medium itself, the stuff that the wave is moving through. And so I have here a picture of a guy with his head on the railroad tracks for a very specific purpose. If you are in the Old West or out in the middle of nowhere and you want to know if a train is coming, it's much better to put your ear down and listen to the tracks than it is to listen to the sound for the train in the air. And the reason for that is because the particles in the steel are very stiffly held in place. So sound waves travel very fast through them. Whereas air, the air particles kind of bounce around. They're kind of not really locked into place in any place, so they transmit sound okay, but not really that great. And it's actually quite slow compared to the speed of sound in steel. And so just to keep that in mind, that the wave speed is only dependent on the medium. It's not dependent on other things like the amplitude. Going back here, the amplitude is the distance between the rest position and the crest, the highest point on the crest, or the lowest point on the trough. Okay, so to wrap it up real quick, the wave speed, though, is determined by this formula right here. Of course, just like anything in physics, you could determine the wave speed by finding the distance that it travels and dividing it by the time that it takes to travel. However, if you know the frequency and the wavelength, it's much easier just to multiply the two together to figure out the wave speed. Why does this work? Because the frequency is in waves per second, and the wavelength is the distance between two crests or two troughs, and so therefore it's the distance for one wave. So we have waves per second times distance for one wave, and so you can see that the waves cancel out. We're left with distance per second. So it works just the same. So hopefully that makes sense. So you can have V equals F times lambda. This little giraffe looking guy is a lambda, which represents the wave's length. So if I go back here, you can see the distance between one crest and the next crest is a wavelength, or between one trough and another trough is a wavelength, or through one complete crest and one complete trough is a wavelength. If I were going to do the same thing with these guys, you could see it's the difference between compression and compression, or rarefaction and rarefaction. It's the same thing. That's the wavelength. So that's the formula that you use for wave speed. It works all the time, hopefully. So no problems with that. If you have any questions on it, please let me know. We're going to be using this formula a lot for sound and a lot for light. So just keep that in mind. It's going to come back again and again and again. So try to get familiar with it if you can. Thanks for watching.